next non-periodic function we're going to take a look at is the impulse function, symbolized with the letter delta, lowercase Greek delta. It's also called Dirac's delta function. And this one has a lot of uses in signals and systems and in digital signal processing theory and beyond. This one's a little tricky because it has a value that, if we look at it in traditional means, diverges toward infinity. But it does have, like a lot of things in calculus in the limit sense, some very useful properties that we'll use in signal analysis. So the key concept with the delta are these two facts. It has area equal to 1, and it has width along the time axis equal to 0. So the problem with this is, does this imply the height diverges toward infinity? And yes, it does. But if we keep these two properties in mind, the area is 1. So if something has area 1, that means if I integrate it, I'm going to get 1. And if we also keep in mind it has a width 0, that's going to be very powerful in a lot of our applications later in the class, and as we derive sampling theory, which is how we go from a continuous waveform to a discrete time waveform. We'll talk a little bit about that toward the end of this class, but that's really a topic that we focus on in the next class, digital signal processing. So if we define the delta more formally, it's defined by two properties. And I'm going to do a time-shifted version here. So the delta is going to be delayed by capital T seconds. So the defining factors are that it has a value 0 almost everywhere. Because that width is 0, it's so incredibly narrow that we say the width is 0 at all the values of t except where the time variable is capital T. So when that argument becomes 0, something else happens. But almost everywhere, if you ask me what is, if I say there is a delta at capital T equals 5 seconds, and you ask me what is the function doing at 4 seconds or 4.9 seconds or 4.999 or 5.1 seconds, anything but that value of 5, the answer is the delta function is 0. So that by itself is pretty simple. And the other property it has is if I take the integral of the delta function, and I'm going to stick with the time-shifted version occurring at capital T here, and I integrate it over the entire time axis, negative infinity to infinity, then the area under it is going to be 1. Now that area, but if we put these two properties together, we see that area has to be concentrated at capital T, because everywhere that's not at capital T, the value of the function is 0. So if I sketch this, if I sketch the delta function, it's 0 almost everywhere. And then I get to t, it goes up to a special type of infinity. It diverges in a particular way at the value t, but then immediately after, it goes back to 0. And it does this infinitely in both directions. So when we draw this upward pointing arrow, it's understood that it has an area here is equal to 1. If there's another area besides 1, we might put a number like 2 or 3 next to it, but in this case the area is 1, so we would draw the Dirac's delta function at time capital T like this. Now, so that's the definition. If I now take the derivative of this, actually, let's do it this way. Let's say let's look at delta of t. It can also be considered, and it is, the time derivative of the unit step, which we are already familiar with. So the unit step, if I draw that out, the unit step, as we know from last time, does this. So now if I'm taking the derivative of the unit step, the derivative here is 0 because this is a flat region. Here, when the unit step goes up to 1, the derivative is still 0, so the delta function captures that. But the additional thing the delta function captures is if I integrate this delta function here, I'm getting no change at these values, no change at these values. But when I integrate over the impulse, over the impulse right there, I pick up area of 1. So the integral of that delta function gets area 1, and I get to the unit step. So if I take the derivative of the unit step, then I get the delta function. So that's another useful property that comes up. Now, before I mentioned limits, and often when we want to see how a delta function looks in the physical world in a real problem, we can't quite go to infinite voltage in the real world or infinite current, but we have models approximating that. Sometimes when we're working a particular calculus problem, if it's difficult how to resolve something, we might use L'Hopital's rule or another approach, but sometimes we want to go back to a definition and look at limits. So there's also a number of approaches to saying the delta function is a limit of another function. And I'm going to show you one model here. There are some fancier ones that have properties that might be useful in certain problems, but what I'm going to do is I'm going to do a triangle, and the triangle is going to be centered at capital T. The area of the triangle is always going to be 1. So we're following this property of Dirac's delta function there and saying the area has to be 1. Now, the base of the triangle, so it's going in the positive and negative direction along there, is going to be 2 tau. So we have capital T plus tau and capital T minus tau are the two edges of the base of that triangle. And if the area is a half of the base times the height, and the area is 1, and the base is 2 tau, then I have the height is 1 over the size, the total size of the base, or 1 over the half width of the base. So the height here is 1 over tau. So now we could write that out as a series of 3 ramp functions. And I will leave that as an extra homework exercise if you want to practice with the ramp function. But we see if I want to write this function out, so it's 0 outside this range. If I want to write this function out, it's 0 up until capital T minus tau, and then there's ramp, and you can calculate the slope of this ramp because we see it gets up to height 1 over tau in tau seconds. So tau determines the slope. Then the slope goes down at twice that rate because it's going to end up going negative and it was going positive. So we have the difference between those. So there's another ramp subtracted at time capital T, and then the function would keep going this way. And finally, we add a third ramp at time capital T plus tau. So we could write that out as the sum of 3 ramps. Now, so we call this the triangle function. This is the triangle function at t minus tau, t minus capital T with a parameter tau. So in a particular problem, we could choose the parameter tau. Now, if we take the limit as tau approaches 0 of this triangle function at t minus capital T with this parameter tau. So we make it narrower and narrower, and the height goes higher and higher. The height diverges toward infinity, but the area is always 1. So this expression here, when I take that limit, I get Dirac's delta occurring at time capital T. So that's our triangle model. So that is it for the definition of this function. Now I'm going to show you next two important properties that we use this function for. First of all is the sampling property. So let's say I have an arbitrary waveform. Maybe this is an audio waveform or some value coming in from a sensor into your system. Now, the idea with sampling is I might want to know what is the value at this exact point in time. And so the delta function allows us to have a mathematical model of that. So let's look at what we do. We take our function x of t and we multiply it by Dirac's delta occurring at capital T, the time we want to sample. So this function right here is an impulse at time t, and it has area 1, so I don't need to label the area separately. So now we have the product of these two functions, and what we do is we integrate it. We integrate the product, and we let the time variable go over all time. So now we can use properties of the delta function to greatly simplify this integral. So first of all, the thing that we're integrating, our integrand here, it's the product of these two functions. One of the key properties of Dirac's delta function is that it's 0 almost everywhere. It's 0 everywhere except when small t is equal to capital T, making this argument 0. So what we can do is we can say this integrand is also going to be 0 almost everywhere. And the only way that it might not be, where we might have some more complications to deal with, is if we would have infinities outside. We'd have to make sure we were handling limits properly, but there are no limits outside. I have a well-behaved real-world signal here, x of t. So the first simplification I make is this. I say, it doesn't matter what the value of the function x is, except at the point that it's being multiplied by Dirac's delta. So I can replace the variable capital T with the constant the variable small t with the constant parameter capital T. And that's the only change I'm making in this step. So that is valid and allowed because it's multiplied by 0 everywhere else. So it doesn't matter what value of x I'm taking. So we'll just take that one value. Now, with respect to this integral, we are integrating over the variable small t, but remember, capital T is a constant parameter. So we can take this x of capital T, and it is just a times a constant, so we can move it out of the integration. And when we show how the sampling property works, that is the next step in our proof. We take it out of the integrand and make it a constant multiplier, and here we are left with this. And now we're going to do a simplification of this term right here. I encourage you to pause the video for a minute and look at your notes, or go back in the video and look at the previous slide and see if you can figure out, based on the properties on the previous slide, what we're going to simplify this to. Okay, let's continue. So on the previous slide, we said that the area under the delta, which is what this integral is evaluating, is 1. So we just have x of capital T times 1 here. So I won't write the times 1. And the sampling property is exactly this. It says this integral that we started with gives us the value of x at time capital T. Now, we know in the physical world we can't exactly realize a true delta function. So when we start designing things like analog to digital converters and we look at their theory in a little bit later in this course and more in the next course, we're going to see some departures from that ideal of looking at just that instant in time and having zero width. But in theory, this is the perfect theory of what we would like an analog to digital converter to do. We would like to be able to take the voltage of the signal X at the exact instant capital T and have a circuit that could do this integral and get us that exact analog value for analysis in a sampled system, sampled time system. And in reality, for a lot of types of signals, we can get very, very, very close to that for all intents and purposes. But we can't quite get there. But that's the theory, and it'll take us quite far. Okay, that's the big property. But I do have one final property for you before we wrap up this video, and that is we have to look at what happens when we time scale the delta. So we're going to talk about the time scaling transformation. Okay, so let's just have the delta at with no time shift, but let's put a scaling factor a here. So for our example, um, I'm going to assume that a is some number greater than 1. This is just for example, but the property we're going to derive will work for any a that's a real number that's not 0. So this will work for basically any a that we might want to use. So remember, if I make a number that's greater in magnitude than 1, when we do time scaling, I've replaced t with at here. What I'm doing is I'm speeding up the function. I'm causing it to occur more quickly. So at a first cut, I still have something that's 0 everywhere. It does something that goes up to some sort of infinite value at the time it occurs, which I have at t equals 0 here. And it's 0 everywhere else. So that's true as far as it goes, but we have to consider what's the area when we sped this up. Now, the original delta, we had, remember, that triangle model. And the triangle model said the area of the triangle is 1, and we represent that as a base 2 tau uh, and a height of 1 over tau. So now what we're doing when we go from the delta to the accelerated delta is we can think of that as compressing the time, so pushing in on the edges by a factor of 2 to make it sped up or narrower. So we're pushing it in, the width is going to decrease, but the height doesn't change. So we move through the delta more quickly, and that's going to cause its area to decrease. So if I want to know what the area of this is, if I have the delta of a t, and I'm going to write negative infinity to infinity, we assume that we're integrating over the entire real line if we don't show the limits often in signals, but I'll put the explicit limits there. And we integrate this over all variables t. What we've done is we've compressed the area. So the area is only 1 over a. And if it's a negative number, I still have positive area because I have just time reversed the triangle here, but it's still a triangle in the positive direction. So we can see time reversal does not change the fact that I have a positive area in this function. So we need the absolute value there for that reason. So that is the time scaling uh, transform of the delta function. It decreases its area, but it does not change that it still occurs at exactly one instant in time. So now this delta does not have an area of 1, so we should label it. We put a little number or symbols representing the area under a delta function next to it. And that's good practice to always do that when the area is not equal to 1. Okay, that's it for our discussion of the delta function or Dirac's delta function in section 1.4.